Now for the third method, not third method, it's a sub-method of the operator method we call shortcut method. For shortcut, they're saying that your fx got to be UC function. Got to be in UC function. What is the UC function? The UC function is the 5 function that we learned in the UC method, undetermined function, which is the power of x, where k got to be positive integer. That is the UC function. 2 is the exponential of ax. A is a constant. 3 is a sine. 4 is a cos function, and 5 is the multiply of either 1, 2, 3, or 1 and 2, or 1 and 3, or 2 and 3, or 1, 2, and 3, and 4, whatever. Now, if so, if you consider that fx is a UC function, then to use shortcut, they are divided into 5 different cases. The first case, when we say that divided into 5 cases, these 5 cases is just divided by, we classify it by take a look at the fx function. So case 1, our fx is the term of the power of x. For the power of x, it's going to be the UC only when the k is just a positive integer. For case 2, it is in the exponential form. For case 3, could be either cos or sine, cosine or sine. Okay, but for sine, you have ax plus or minus b. A cannot be 0, because whenever a is equal to 0, that side of that angle got to be a constant. So for the constant, you can take it as a case 1 or case 2, right? So that's why for case 3, I'm saying that a and b are constant and a is not equal to 0. For case 4, your fx got to be in the form of exponential of fx times vx. And your vx got to be UC function only. So that means your x can be power of x, can be sine, can be cos. Can your vx is equal to tan x? Can your vx be tan x, tangent of x? No, because tangent is not UC function. Can be natural log of x? No, because natural log of x is not UC function. And case 5, your fx got to be in the form of x times vx, where your vx got to be UC function. So if you have other functions, not matching with any case 1, 2, 3, 4, cannot use this method to find the yp of your differential equation. Now, let's take a look at our case 1. So each cases will have different methods to find yp. So if you figure it out that your function matching with any case in here, just use that technique to find a solution. Saying that when you write down, like I said, this one is still inside the topic of find yp by using operator d. So when you have your differential equation, you get to write it down in the term of operator d. And then at the end, you would get that your yp is equal to 1 over pd times x to the power k. It's a power function of x. It's saying that you have to write down the term of 1 over pd in this form. Where the differential of fx at the k plus 1 times is equal to 0. What I mean by this sentence? This sentence means, for example, I can give you example. If you have x to the power k is x to the power 3. When you do the first differential of x to the power 3, what do you get? When you do the second derivative of x to the power 3, what do you get? When you do the third derivative of x to the power 3, 6. When you do x to the power 4, 0. And if you go higher to the power n, you still getting all around here 0. Now, if your k is equal to 3, any time that you do differential, if it is greater than the third time, they all become 0. So that means the rest of the term right here will become 0, right? Because when you do 1 over pd to be this form, you would find that it never ends. You will have the differential to the number n, to the infinity. But what I try to say is, since the meaning of the derivative, it just makes the rest of the term, the number greater than k, become 0 from this result. So let's take a look at the example. Now, this differential equation is in the form of non-homogeneous differential equation. So the solution would combine with yc and yp. Now we find yc. The characteristic equation is this one, right? So yc is equal to, now we find yp. We don't want to using the successive integration or partial fraction integration. We want to try to use the shortcut method to do it. Okay. So from this one, if you want to use the successive or partial fraction integration, you can do it too. But the thing is that when I take a look at that, I know that no matter what technique you use, you still got to do by part integration technique because I have x squared there. So instead of using this, because I'm not good at doing the integration, I said that, okay, I'm going to use the shortcut method. Okay. In order to the shortcut method, you got to write down your y in the term of y is equal to 1 over PD times your fx. Okay. So now we write down the differential equation in the term of operator d. So you would get like this. And then I say that, okay, I know that x to the power 2 or x squared, it is fitting with our first case, which is the power of x. So I'm going to find yp by using the first case of the shortcut. It's saying that if we have 1 over pd, we are going to write it down in the term of b0 plus b1d plus b2d squared plus into bkd to the power k. Now, the first term, 2, actually we have the function of power x, right? It's 2 times x to the power 0. Okay. And so that means the first term, our k is equal to 0. And the second term, our k is equal to 2. So write down the 1 over pd in this form is saying that the way to do that, your pd, you got to rearrange the term by starting with the constant. For example, put a0. You got to write down in such the way that your d is go from d to the power of 0 to d squared and so on. Now, our PD is d squared minus 1. So in this case, we got to write down our PD like this, minus 1 plus d squared. Okay, so that means if we rewrite it, we would get and then how do we write this term into this? It's just simple. We do the dividing. What times minus 1 equal to 1? What number times minus 1 equal to 1? Minus 1. And then get 1. You got d squared. What time minus 1 equal d squared? Minus d squared. What times minus 1 equal to d to the power 4? Minus d to the power 4. And we can do more and more and more, but I said, no, I don't want to go this far. I stop right there. We said that, okay, if we rewrite this term, we would get minus 1 minus d squared minus d to the power 4, and it's not n, and so on. But I think that, okay, just stop right there, because if you take a look at this, the first thesis that I say, actually it should stop at x to the power k. And now you have your first x to the power k is 0, and the second term is x to the power 2. So actually it should end up at c squared. But I wanted to go further a little bit in order to tell you that why we got to stop right here. Okay. And the next thing is that we do distribute the term to each of our functions. Right? And then you distribute your function to the term of your differential you would get. The first term you got minus 2, minus c squared 2, minus c to the power 4 2, and so on. And this one you would get plus x squared plus b squared x squared plus b to the power 4 x squared, and so on. Now, what is the second derivative of 2? 0. What is the fourth derivative of 2? 0. So this 0, what do you think about the whole term, the rest of the term? 0, they're all 0. What is the second derivative of x squared? 2. What is the fourth derivative of x squared? 0. So how about the rest of the term? 0. So that's why when you write down the 1 over PD, it's saying that you stop at the k derivative of the function. Because we know that for the higher number of that, you would get the rest as 0. And this would work only when this function is the power function. And it's got to be the positive integer for that function too, right? Because if you get negative, for example, if this x is 1 over x squared, so you get x to the minus 2. When you do the first derivative, you would get minus 2 times x to the minus 3. If you get the third derivative, instead of going to 0, it's not. The power of x is just getting more and more and more. So that's why it won't work if your k is a negative integer. It works only when your k is a positive integer. So your yp is equal to x squared. Now, the answer would be y is equal to yc plus yp, which is c1 times exponential of minus x plus c2 times exponential of x and plus x squared.